Okay. So now we do logarithms, right? So logarithms and their graphs. Logarithms are a new kind of function that we might not have dealt with up till now. I mean, you did some of it. You did some of it in Algebra 2. Truthfully, most of the stuff we do today is the same stuff. It's the stuff that comes after this, which probably goes into territory that you had not seen very much. Because we didn't do much solving of equations in Algebra 2, of solving of exponentials and solving of logarithms. We did most of the stuff about the graphs, the fact that they're inverses. All that was part of Algebra 2. Okay, so logarithmic functions. They are just a different way to express the relationship that you see in an exponential. So if you say 2 to the third equals 8, that's an exponential expression or equation. Sorry. That's the same thing as saying log base 2 of 8 equals 3. You just rearrange everything's position and you've got it. So notice that the base, there's this number right here that comes after the logarithm. That's the base of the logarithm. It's a subscript. It's a little bit smaller and it's written down a little bit. That's the subscript. That's the base of the logarithm. So the base of the logarithm is the same thing as the base of the exponential, right? These are the same. And the logarithm itself equals the exponent that that base was being raised to. Right? So the logarithm equals an exponent. Right? Logarithms equal exponents. There will be a few homework problems that say just rewrite, take something like 4 squared equals 16 and write it as a logarithm. And how would you do that? Log base 4, right? This is the same. All right. It's going to equal the exponent, which is 2. So you're taking the log of 16. Right? In your mind, what you're asking yourself when you see a logarithm like that is, what power would I raise 2 to get 8? 3. What power would I raise 4 to get 16? 2. Right? That's what a logarithm is. Right? So with that same kind of thinking here, what power would I raise 2 to get 32? What's that? 5. Right? 2 to the 5th equals 32. What power would I raise 3 to get 1? If you want to look at it in the exponential form here, 3 to what power equals 1? 0. Anything to the 0 power equals 1. Right? What power would I raise 4 to get 2? 1/2, right? You got to think of that as to the 1/2 power. 4 to the 1/2 is the square root of 4. So that's your 2. Right? What power would you raise 10 to get 1 over 100? Right? Think of it like this, right? This is 10 to what power equals 10 to the minus 2. Right? 1 over 100. If it's 100 in the denominator, let's say 100 is 10 squared. And if it's a 10 squared in the denominator, it's a 10 to the minus 2 in the numerator. So what power do you raise 10 to get 1 over 100? Negative 2. Okay, negative 2. So bottom line, logarithms are exponents, right? Logarithms are exponents. So the properties of exponents are the properties of logarithms. And I think the next section is properties of everything, dealing with how we deal with logarithms. There's some in the lesson today. But for example, when I'm dealing with exponents, this was one of our properties of exponents. 10 to the second power times 10 to the third, right? When you're multiplying the same base raised to different powers, what do you do to simplify? You add the exponents, right? So you get 10 to the fifth. Well, it works similarly with logarithms, right? Log base 10 of 100 times 1,000 can be split up into the log of 100 plus the log of 1,000, right? So we're able to use logarithms because they have the same kind of properties as exponents. We're able to turn a multiplication problem into an addition problem. And that's where logarithms had their start, right? And it's about 1609, a guy named John Napier is the guy who came up with this. And if you can imagine, in those days, that was right in the time, in between Copernicus and Galileo coming up with, with their idea that the sun is actually the center of the universe and studying the orbits and all that. I mean, think of the calculations they had to do back then, and they didn't have any technology to do it. They probably had a bunch of monks sitting at a table in a castle somewhere, and it would take years to come up with anything meaningful. But when they came up with the idea, well, what if we could just make a table where all we do is say, what power would I raise a common base to get this number and this number and that number? We'll just have a whole big table of logarithms, exponents. And we'll just deal with the exponents. We won't deal with the actual numbers. Then when we have to do a multiplication, we'll turn it into an addition. And that made a big difference. I mean, try to think of the numbers involved. What's the distance from here to the sun? And you're trying to calculate an orbit or trying to detect, like they did back then, the difference between a completely circular orbit and the really slight elliptical orbit that the Earth actually has around the sun. I mean, if you saw it traced out, it would be impossible for you to detect. But they detected it. They detected it by doing calculations that they couldn't do before, but they could do once they had logarithms. Right? So that's where logarithms came up, because they were able to turn multiplication into an addition problem. Okay? And the first logarithms they did were base 10. Right? But quickly, there became other logarithms that they used. But the first guy was named John Napier. We used to have some students here, last name of Napier. In fact, one of them was named John Napier when I first started working here. Okay, so the log base 10 is called the common logarithm. And if you don't see a base written, it means log base 10. So on your calculator, if you look on the keypad over here, right, there is log, L-O-G, and it does not say the base. So that means it's log base 10. Okay, so just to show how you use the calculator to do it, if we really need to. If you want to take the log of 275, you go log, and then you call the number that goes inside the argument of the function, right? So the argument is 275, and we get 2.439, right? That's the power you would raise 10 to get 275, which makes sense. I mean, 10 squared would be 100, and 10 to the third would be 1,000. So it's got to be in between those two, because this number is in between 100 and 1,000. Right. Now, see what it looks like if we do 0.275. Log 0.275. Okay, now we got it's negative 0.56. Get all that right. Now, see what happens if we do the log of negative 1/2. Log negative 0.5. What I got wrong here? Just a second. You got to make your mode real, because that should not have worked. Okay, second, enter. The log of negative 0.5 is an error. Should be a non-real answer. Which is going to bring up till now, when we did domains, we always said, don't divide by a 0. Don't take the even root of a negative number. And now we're going to have a new restriction. Logarithms do not have an unlimited domain. And when we see the graph, we'll see why that is. So this one is undefined. Okay, so there are properties of logarithms, and most of these properties relate to exponentials. That's why, just copying this out of the book, there's one column with the property of logarithms, and then they convert it to an exponential form, and you see that it's actually something. It's a relationship you already knew about exponentials, just written as a logarithm. So, for example, the log base A of 1 equals 0, meaning A can be any positive number. So that means the log any base of 1 equals 0. Well, if you convert it to an exponential, remember the base of the logarithm is the base of the exponential. The logarithm equals the exponent, so that 0 goes there, and then the argument goes on the other side. So A to the 0 is 1. We already knew that anything to the 0 power equals 1. Well, saying log base A of 1 equals 0 is saying the same thing, just in a different way. Right? They're just two different ways to express the same relationship. Okay, the next one here, right? This one is especially important right here. Right? The log base A of A to the x equals x. Okay? And what's important here, you're taking the logarithm of an exponential, right? The base of the logarithm is A. The base of the exponential is A. When you do that, the log base A of A, all that cancels, and whatever the exponent is, that's what it equals. So we use that all the time when we're simplifying. That's how we go about, for the most part, that's how we go about solving logarithmic equations, by taking advantage of that property. Now, if you go to the second one is really saying the same thing as the third one, just for one particular exponent, right? Log base A of A, well, what's the exponent on this A? It's a 1. So whatever is that exponent, that's what it equals. Right. And then this last one, which we will use to solve equations like we did the exponentials, the one-to-one property. If you can write a log on one side equals a log on the other side, and they've got the same base, then it must be that their arguments are the same, right? If the left side equals the right side and they're both log base A's, then x equals y. So if you can ever get that set up, then you can solve the equation. Right, so these are examples of properties. So how would this simplify? Log base 9 of 9 equals, that would be this property right here, right? Because the base of the logarithm and the base of the exponential match up, so it is 1. Okay, simplify. 20 to the log base 20 of 3. That would be like the second part right here. 20 to the log base 20 of 3 equals 3. Simplify. The log with a base of the square root of 3 of 1 equals 0, right? Because the log of 1 of any base is always 0. So it's 0. Even with a crazy square root of 3 as a base, which we'll probably never see, it does not matter. Any base, that's the answer. You know, we'll use these later on when we're solving equations. That's 2 sections down the road. I usually don't end up using that one. I mean, in the end, I mean, you can think of it like that when you solve them, but you'll see there's another way to think of it, which is probably the way you're going to think of it, which is equivalent, but that's why I didn't say much about that at the beginning. Okay, and here's a solve. This is using the fourth property, right? The one-to-one property, which is similar to the one we did. This was the one-to-one for exponentials. if a log base 5 equals a log base 5, then what do you know about the arguments of those logarithms? They're equal. So you make an equation. X squared plus 3 equals 12. Right? Subtract 3. X squared equals 9. X equals plus or minus 3. Okay, that's one-to-one property because it's just clearly one log on the left, one log on the right. They have the same base, right? Then you make an equation out of the arguments. No more logarithms. Okay. Now, let's go through the steps to find an inverse, right? Normally, we would say first step is replace the f of x with a y. The second step is switch the x and the y. And then the next step is solve for the y. But the y is inside the logarithm, right? So we can't divide by the letters log. So instead, we're going to convert it to an exponential, right? What will the exponential look like? The base of the exponential will be a. The exponent of the exponential is x, which makes y equals a to the x. So by converting it to an exponential, we did solve for y. Right? So then the last step would be replace the y with an f to the minus 1. F to the minus 1 equals a to the x. Right? So what we learn from that is actually logarithms and exponentials are inverses of each other. They are exactly inverses of each other. So logarithms and exponentials are inverses. So for example, f of x equals 2 to the x is an exponential with a base of 2. Its inverse would be the logarithm base 2 of x. So now all those things that we know about inverses become true about logarithms and exponentials. Right? The domain of the exponential function then is the range of the logarithm. The range of the exponential is the domain of the logarithm. They swap, just like we swap the x and the y. The graphs, if you graphed them on the same background, they would look like they're symmetric with respect to the line y equals x. And those are just what we know in general about any function and its inverse. So that's what we know about these two. Now just think for a second. Normally before we find an inverse, what's the test we do to make sure it has an inverse? A horizontal line test, right? So remember, if you're looking at that function as being the original function, that's exponential growth. So it looks like that. Does that pass a horizontal line test? Yeah, it does. So it definitely will have an inverse. And we just saw, and the inverse is the logarithmic function. We're good? Zach? I don't remember what's there. So again, it should look like the graph of the exponential and the graph of the logarithm are reflections across the line y equals x, which is right here. Now remember what we've already studied the exponential function some, right? We know that the domain of the exponential is all real numbers, right? All reals. Right? That means that the range of a logarithm is all reals. Remember what we said about okay, before we go to the range, where is there an asymptote with the exponential? It's on this axis right here, right? We knew that the exponential can never equal 0, right? 2 to whatever power. There's nothing you can substitute for x that makes that function equal 0, which means it's never going to touch the x-axis, which means y equals 0 is an asymptote, which meant that the range of this function was y greater than 0. Okay, well that means that the domain of the logarithm is x is greater than 0. Right, so here's the logarithm. Its domain is x greater than 0. And it also has an asymptote there. X equals 0. Remember the exponential had a y-intercept of 0, 1. That means the logarithm has to have an x-intercept of 1, 0. So this is 0, 1, and this is 1, 0. Okay, so just focusing on the graph of the logarithm, that's why we can't take the logarithm of a negative number, because the graph does not go to the left where x is negative. I mean, you can't even take the logarithm of 0, right? Because it never touches the y-axis. You cannot say logarithm of 0, right? So you can't do that, and that's why. So when you talk about domain, you have to be a little more careful with the logarithm function. It does not have an unlimited domain. Exponentials, you can plug in anything you want. Now, the normal exercise at this point is to say, okay, let's graph log base 4 of x, and then say to ourselves, well, I don't have a log base 4 button on the calculator, so instead, let's graph 4 to the x, because that I can make a table of values for, and then switch all the x's and the y's, and therefore I can graph. But the truth is that since we used to do that, these calculators now let you do the logarithm of any base. So, I mean, I don't want to really play that game. In the end, you're going to use your calculator to find logarithms of any base, right? Here's where you find it in your calculator, right? 1, clear. Right, so I already entered in the calculator log base 2 of x and log base 4 of x. So here's how I did it. Clear and clear. Go back up. Right, I go to the math and then scroll all the way to the bottom, log base. Right, so go up to that one, hit enter, and then you can enter in whatever base you want. So we're not restricted to the log base 10, which is on the front of the calculator. You could do whatever you need. So that's what I did on this one, just to compare, like I did with the exponentials. Does it change the shape of the graph much if we change the base? I mean, this is log base 2 of x, and that's log base 4 of x. This is the normal view in the calculator, where the fat line is the log base 4, and this is the zoomed in version of it. But, you know, it's the same basic shape. The asymptotes are in the same place, right? The asymptote is still here, right? I just show it right here. The x-intercept is still 1, 0, right? The domain is x greater than 0. And one thing to keep in mind here, especially when you look at the zoomed out version right there, it may not look like it, but that has a range of all real numbers. Remember, it's the inverse of an exponential, and it has a domain of all real numbers. So even though it's going up very, very slowly, it's still going up, and it will go up infinitely. So don't look at the graph like that and start to say, because this happens all the time. You guys will look at that and go, oh, it looks like there's a horizontal asymptote here. There's no horizontal asymptote. It will eventually go above that line. Whatever line you put on there, it'll eventually go above that line. But it's going to go slowly, right? It's like, again, when we talk about exponential growth, that's like the flip of that. It's logarithmic growth is like very, very slow growth, although nobody ever uses that phrase. So we don't worry too much. Most of our formulas have an A in there, and the A is just some number, right? And we don't worry so much about the number. The properties are all the same. Domains are the same. Ranges are the same. Intercepts the same. Everything else is the same. So we don't get hung up on that part. Okay, and also we can do transformations of those graphs, right? On both of these graphs, there's the logarithm of x. And what base is that? It doesn't have a base, right? So that means it's log base 10. And for our, it really wouldn't matter because the shape would be all the same anyways. So what happens to that graph when I subtract 1 inside the function? What always happens when you subtract 1? It goes to the right one. And that definitely goes to the right one. Okay, does that move the asymptote? The asymptote was here. If you move the whole graph to the right one, does it move? Sure it does. So the new asymptote is here. Right. So now the asymptote is x equals 1. What is the new range? Remember, the range was domain. What is the new domain? It used to be x greater than 0. Now it's x is greater than 1. Right. So the range is x greater. I keep saying that. The domain is x greater than the range is all reals. That doesn't change. Right. What happens to the graph when we add a 2 outside of the function? It goes up 2, right? So this graph goes up 2. Every point on this graph is 2 higher than the graph on the log of x. Okay, does that change the asymptote? If you take a vertical line and move it up 2, does it change? No, it's still the same line. So this would have the same domain and range. It only changes the domain when you have a horizontal shift. Then that changes the domain. Okay, so remember from last lesson, E is an irrational number approximately 2.71828 ... never terminates, never repeats. We call that the natural base. Okay, the logarithm that uses E as the base is called the natural logarithm, and it's written as ln of x. Right? You don't see a base there, but when you see the ln, you know it means the base is E. Right? So if you go to your calculator, right below the logarithm, there's your ln. Right? Natural log. And the truth is that when you go in math and science, ln is used so frequently, you don't say natural log, you just say log. Everybody knows what you mean. It means ln. There's very few applications that I know. The one they always give for log base 10 is the Richter scale in earthquakes, which is somewhat contrived scale. But in what happens in nature, the things we study, ln is almost always the logarithm that you use. Like I said, so much so you don't even say natural logarithm. You just say log this, log that. Everybody knows what you mean. Okay. So all of the properties that we had for logarithms are really just repeated for natural logarithms, because when we had the properties for logarithms, they were for log base A, and A could be anything. So now all this is saying, okay, let's let A be E, right? But it looks a little different because when you look here, you don't see the base, right? So that's E to the 0 equals 1. That's how it looks like as an exponential. And we'll be doing these conversions all the time. When we're solving the equations, that's just part of how you do it, right? E to the first equals E. That's what that is, right? E to the x equals E to the x. Right? So those are the only three that works on. But anyways, the properties are still the same, right? When you take ln of e, then you're matching the base of the logarithm with the base of the exponential, so it equals whatever the exponent is, right? That's why that is the answer, right? When you take the ln of e by itself, it's still the same property. It's just that now the exponent is 1, so that's why it equals 1, right? Ln of 1 equals 0, because e to the 0, anything to the 0 equals 1. And the same one-to-one property that we used to solve a logarithm before would work if there were natural logs on both sides. So let's see. Using the properties, what is ln of e to the 1/3? Hey, come on in. Okay, everybody's here, so okay. For 10 minutes ago. What is ln of e to the 1/3? 1/3, right? Equals 1/3, right? Because ln of e cancel each other out. I mean, now that, because we did that part about showing the inverses, we can understand now what's going on here. When you take ln of e, what you're doing is you're doing f of f minus 1. It's the composition of a function and its inverse, which by definition gives you x. That's all that's going on here. We're taking a composition of a function and its inverse. First, we take the log of the exponential, and then we take the exponential of the log. It doesn't matter the order. When you take a composition of a function and its inverse, you get whatever's inside the function, x. Okay, what about this one here? 5 times the ln of 1. Okay, well, ln of 1 is 0, so it's 5 times 0, which is 0. How about 3/4 times the ln of e? The ln of e is 1. So it's 3/4 times 1, which is 3/4. And e to the ln of 7, that's this thing right here. E to the ln of 7 is 7, right? Again, that's just taking a composition of the exponential and the logarithm. And since they're inverses, they cancel each other out and you just get x. So you really don't need properties of natural logarithms, because the other one was even more general. It said logarithms of any base. So of course it would work if you substituted. The only thing that's different is now you're not looking at something that says log, you're looking at something that says ln, and you're supposed to recognize it for what it is. Okay, so find domain. The ln of x minus 2, right? What is the shift when you take away 2 inside the function? Goes to the right 2. So what happened to the asymptote? It moved to the right 2. So here's the new asymptote, x equals 2. So the domain is x is greater than 2. This one is kind of a funny one, right? So let's see, if there 1, 2. You know, what are the things that are going on inside of that one? What does it normally do when you put a minus in front of the variable? A reflection in the y-axis. So this thing is not going in the same direction as all the other logarithms. It's going in the opposite direction. Okay, but normally we would expect if you add 2 inside, so that should have shifted it which way? To the left, right? In this case, it's clearly not. And you can check to see if it's correct or not. I mean, first, the ln, it should be at x equals 2 that this thing has its asymptote, and it does. It should be that if you substitute x equals 1, you get y equals 0. Okay, we put in a 1 there, you get 2 minus 1 is 1. ln of 1 is 0, so we got the right asymptote there. So this is in the right spot. It's probably would look a little different if we did it like this. G of x. I get in trouble doing this sometimes. Equals ln of negative x minus 2. So the x minus 2 shifted it 2 to the right. The minus made it go the other direction. Okay, so this one, what is the domain? X is less than 2. Okay, don't think in whole numbers. Don't say X is less than 1. What about all the points on this graph that are in between 1 and 2? X is less than 2. And then this one, that's a funny graph, right? ln of x squared, right? So let's see. You can't take the logarithm of a negative number, and you can't take the logarithm of 0. But if you're squaring, doesn't that make everything positive? No, there's one number that does not become positive when you square it, 0. So this thing still has the asymptote right here. But you can plug in both positive x and negative x, because when you square it, right, it'll be positive. So you can take the logarithm. So what is the domain of this one? X does not equal 0. Okay. So then one more thing. You're going to have a word problem pretty much like the one we had for exponentials. There's a 3-word for exponentials. I mean, at this point, we have not talked about solving logarithm graphs or solving exponentials, right? So there's a limit to what we can do, right? I can't give you something where you solve for the exponent or solve for a variable that's inside the logarithm. We'll get to that. All we can really do is evaluate these functions. All you can really do is just plug in and see what you get. I mean, this one says students participating in a psychology experiment attended several lectures on a subject and took an exam. And every month for a year after the exam, the students took a retest to see how much of the material they remembered. The average scores for the group are given by the human memory model. F of t equals 75 minus 6 ln of t plus 1, where 0 less than or equal to t less than or equal to 12. T is the time in months. So what is this telling us now? It's domain. Remember, whenever you get the function and then it says comma and it gives you some values, like remember the piecewise functions or whichever, that's telling you the domain. It said only plug in months from 0 to 12, and then this thing will work. Okay, so what was the average score on the original exam? Okay, so if you plug in the t equals 0, you're taking the ln of 1, which is 0. ln of 1 is always 0. So that means this whole second term goes away, and all you have is the 75, which makes sense because at the beginning, that was your first score, was 75. Okay, now, as the months get bigger, you're going to be subtracting more and more from the 75. Okay, what was the average score at the end of 2 months? How were you supposed to find that? All right, you're going to plug in 2 here, right? So that one will look like this. F of 2 equals 75 minus 6 ln of 2 plus 1, which is 75 minus 6 ln of 3. And what is that? $68.4? Sounds about right. 68.4. 68.4. Okay, do it again. 6 months. F of 6. 75 minus 6 ln. I'm going to skip a step and just say ln of 7. Say it again. 63.3. Now, could you plug in a value bigger than 12? I mean, according to the problem, it says this is valid from 0 to 12. Don't plug in values bigger than 12. I mean, there's nothing wrong with that equation in terms of plugging in a number bigger than 12. It's not going to become undefined or anything like that. It's just that somebody, whoever did the research on this thing, they came up with this model and said it's valid from 0 to 12. So don't try to use it. Don't try to like plug in 24. I mean, there's going to be a point when it reaches 0, right? And you wouldn't want to be predicting negative values because you couldn't go less than 0. Okay. So I think there's one problem like that, something like that. Again, don't be intimidated by the word problem. In the end, all you're doing is evaluating. So that's really all we can do at this point. So recognize and evaluate logarithms with a base A, right? Graph logarithmic functions. Recognize, evaluate natural logarithm functions, base E, and then use logarithms to solve real-life problems. And there's a lot of problems in there, but you got 35 minutes. I bet you'll be almost done with it by the time you leave here, because I know you're going to work, right?